study of Parareal with MGRIT and shallow water equation on the right. Please.
So this work is is in collaboration with Pedro Peixoto, also from the University of São Paulo, and Martin Schreiber from Grenoble. So, so here we are solving numerical simulations for atmospheric modeling. And it's quite hard to find a compromise between accuracy, stability, and computational cost. So here we are focusing on the Charlotte equations on the sphere. So we have different stability constraints related to different physical processes. So we have, for example, CFL, stability conditions related to fast gravity wave propagation in stiff linear terms of the equations, and also due to advection. So we need to seek for more efficient computation approaches. And parallel time methods is a possible candidate for doing this. Well, however, in general, operational codes in atmospheric modeling are quite complex. So it would be useful to use non-intrusive approaches such as Parareal and MGRIT. But we know that due to the hyperbolic nature of the equations and also to the existence of waves propagating at different speeds, we may expect to have some difficulties in terms of stability and convergence. Well, this work started like 2-3 years ago, which we have presented here in this workshop in 2023, when we had some promising results using Parareal and MGRIT combined with semi-Lagrangian exponential methods, which are quite new type of time integration schemes, which were proposed by Peixoto and Schreiber in 2019, which combines a semi-Lagrangian treatment of advection with exponential methods for the linear terms. So this kind of method is able to handle with stability both advection and stiff linear terms in the equations, such as the Charlotte equations. However, we soon realized that we need to take a step back in this research. So first, as I said, computational codes in atmospheric modeling are quite complex. So before trying to formulate a new method, it would be useful to verify if we can do temporal parallelization using methods that are already implemented operationally. And also, before developing a new scheme to temporal parallelization, it's necessary to understand better its properties in the zero framework. So to understand the convergence and stability properties of the method. So we have split this research into two directions. The first one is a parallel time one, which I'm presenting here, in which we study temporal parallelization using existing time integration schemes in operational contexts. And a second direction is a serial one, in which we try to understand and solve some issues concerning the order of convergence of semi-Lagrangian exponential schemes. So to give some examples of operational integration schemes using atmospheric models, we have, for example, explicit methods, in which the linear terms of the equations are integrated implicitly. And it's used in climate and numerical weather prediction agencies, for example, in the US. And also we have semi-Lagrangian methods. So the idea is to, instead of relying on fixed spatial grids, is to estimate the trajectory of the particles of the fluid a long time. And we have, for example, a very popular method, the semi-Lagrangian semi-implicit settle scheme, which is used in the European forecast model and also in the US. And recently there are some works trying to use this idea of semi-Lagrangian treatment of advection inside a temporal parallelization. So so the goal here is to investigate if we can if operational atmospheric models can be parallelized in time. So more specific, if Parareal and MGRIT using S-course schemes. Time integration schemes that are used operationally can be successful in terms of stability and convergence. So we do this through some analytical stability studies and also through numerical investigation of convergence, stability, and speed up. And also we try to see if it's possible to improve the results. So more specific, we want to check if we can use level-dependent hyper-viscosity approaches to improve these results. So first, this analytical stability studies is a classical linear stability analysis. So we have an OD with a linear and a nonlinear term, which is linearized. So we have some kind of Dawkins test equation. And here we have these two modes, lambda L is associated to the linear mode, and also lambda N, which is associated to the nonlinear function, to the linearized nonlinear function. Well, for this, when apply some scheme to this equation, we can write this into this form. So we have here this stability function, this amplification factor, which links the solution between two time steps. And we define the stability region as the region in the C2 space in which this stability function has a absolute value not greater than 1. And here, here this stability study would need to be done in a 4-dimensional space because both modes are complex. But to simplify this study, we're going to fix the linear mode and the stability in terms of the complex and the real part, the imaginary and the real part of the nonlinear mode. So here consider two cases, lambda equal to 0, which corresponds to well, in fact, to geostrophic modes in the linearized Schwarzschild equations, or to slow Rossby waves in on the sphere for the nonlinear equations. And also lambda L equal to 5 times the imaginary unit, which corresponds approximately to the fastest wave in a reasonable discretization using 256 modes and a time step of 8 seconds. Well, this formulation of a stability function can be extended to parallel time methods. So following the work by Staff and Ronquist, we can formulate a stability function for Parareal. So we can write the solution iteration k and time step n as a function, as an amplification factor times the initial solution. And this amplification factor depends on the established function of the defined propagator, AF, and also the established function of the closed propagator, which uses a time step delta t, which is MC times the defined time step. We can also do a similar approach to obtain a established function for MGRIT. So specifically in the case of two-level MGRIT with an arbitrary relaxation. So here we have a similar expression with a established function depending on the established function of the fine and the cost solvers, but depending also on the relaxation parameter. So to give some examples of these stability regions, so here we have the stability regions for Parareal along iterations for the slow modes. So here in the left, here the fine scheme is the implicit explicit, and in the left we have the simulations using IMAX as cost solver, and in the right using the semi-Lagrangian scheme. So we see that in both cases the stability region decreases along iterations. So in fact, the stability region at iteration 0 is equal to the stability region of the course solver, the serial course solver, and along iterations we have a decrease of this stability region. If you consider now the fast wave, we see a similar behavior for when we use IMAX as solver. But in the case of the semi-Lagrangian scheme, we see that we have a much stronger reduction of the stability region. In fact, after 2 iterations, the stability region is empty. Now, if we look to the stability as a function of the relaxation parameter in MGRIT, we are also in this case of the fast gravity wave. And we see that when we increase the relaxation, we are able to increase the stability region. So after with a parameter, a relaxation parameter of 5, we can recover the stability region of the cost series scheme. And the same case for the semi-Lagrangian scheme. So after with relaxation parameter equal to 2, we have a non-empty stability region, and with 5 we can recover the 0 stability region. So now with some indications in terms of numerical results. So I'm doing simulations here using this test case in which we have so it's the Charlotte equations, the rotation sphere. We have this initial solution with 3 Gaussian bumps on the geopotential field. In space, we solve the equations using a spectral discretization with using spherical harmonics. The simulations are done for 1.5 days. And in the final level, we use IMAX with a small time step of 1 minute. And in the cost levels, use either IMAX or a similar Lagrangian scheme with a coarsening factor MC to define the time step on the cost levels. And for now, we are using, in this moment, we are using a fixed artificial viscosity of second order, only on the cost level. So on the final level, we don't use viscosity. So here we have a convergence plot showing the errors between the parallel time and the final solution when we use IMAX on the cost level. So we see that, well, the results are not very good. So in fact, the only relatively stable simulation is these blue curves, which corresponds to simulations when we have 2 levels and a cosine factor in time of 2 between the final and the cost level. So it means that the cost time step is 2 times larger than the final time step. So it's the simulation with the smallest time step on the closest level. So we are able to keep the simulations relatively stable. On the other hand, if we take the simulation with the largest number of levels and the largest cosine factor, have the largest time step on the closest level, and the established constraints are just too hard. So we are not able to complete a single iteration of Parareal, of MGRIT in this case. And we also have some results indicating the influence of the relaxation parameter. So each pair of curves using the same color corresponds to the same configurations, but with a relaxation parameter of 0, responds to Parareal, or a relaxation parameter of 5. We see that we don't see much difference between these 2 parameters. We have some smaller errors here in the blue curve when we increase the relaxation, but it's negligible. So we don't have much influence of the relaxation. So these results are using IMAX on the cost levels. And when we use the same Lagrangian scheme, it's even worse. So we see that even when we use a very small time step on the cost level, we don't have stable simulations. So just to give some ideas in terms of physical solution with we obtain. So here we have the solutions. Oh, so this slide's in the wrong position. We'll just talk about the viscosity first. We'll come back here to this slide. So before showing this physical solution, so here in these old simulations, we have used a fixed second order viscosity. So it means that we are maybe dumping too much the solution. So the idea here is to try to see if we can use higher order viscosity So it means that we're able to dump only the largest wave numbers of the solution. So we can keep a relatively accurate solution. So the questions we're trying to answer here is if it's necessary to use viscosity on all levels of crystallization, which order of viscosity and which coefficient need to be considered, and if we need to use the same viscosity on every level of crystallization. Of course, the goal here is to keep the viscosity as small as possible. And to do this study, we are fixing the number of levels. So we have 3 levels for the distillation. On the finest level, use Imax with no viscosity. So we have the accuracy of the finest discretization. And on the cost levels, use either Imax or the semi-Lagrangian scheme, using viscosities of order 2, 4, or 6. And we have this plot. So here, each small square corresponds to a simulation, and the color indicates the error that's within after 10 iterations. Here using Imax on the cost levels. Well, the red squares correspond to simulations which are unstable, so we're not able to complete them 10 iterations. So here in the horizontal axis, we have the viscosity on the second level. Here we have 3 levels. So the viscosity on the second level is the horizontal axis, and the vertical axis is the viscosity on the third level, the coarsest one. And we see that when we have small viscosity on the coarsest level, so here, for example, have a small second order viscosity or a small fourth order viscosity, we have unstable simulations. And the smallest errors are obtained when you use large fourth or sixth order viscosity on the coarsest level, almost independent of the viscosity on the intermediate level. So we see that's sufficient to in order to control the instability, is sufficient to choose a fourth or sixth order viscosity in the coarsest level. If we do the same studies using considering the similar Lagrangian scheme on the coarse levels, we'll have some similar results in terms of using too low viscosity, so we just have unstable simulations. But contrary to the previous figure, we see that when we use higher order viscosity on the coarsest level, we have larger errors. So in this case, using the same Lagrangian simplicity scheme, we have more instability, and it's not enough to dump only the largest the largest numbers. So in order to have relatively small errors, we need to use second order viscosity. So we need really to dump a large amount of the wave number spectrum. So just come back to the other slide here. So to give some examples on this result. So here we have the viscous solution obtained using Imax on the course levels with a 6 order viscosity. So we see that after 5 or 7 iterations, we are able to have a relatively good representation of the reference solution with well, some modest speedups using here 64 processors. But in the case of the similar simplicity scheme, we see that we have largely diffused solutions because we need to use second order viscosity. And also the speedup is even smaller because the semi-Lagrangian scheme itself is more expensive because we need to interpolation and for estimate the trajectories of the solution. So well, as a final application, so here was for this test case with the Gaussian bumps. So here we are considering a more challenging test case. We have seen this yesterday. Is the Galeowski unstable jet test case. So we have a quite simple initial solution, but with a small Gaussian perturbation on the geopotential field. And after a few days of simulation, we have a much more complex dynamics. So here we make the simulation up to this period of time to 6 days with IMAX on the cost levels using a, a time step of 1 minute and no viscosity. And on the we're doing two level parallel time simulations using IMAX or semi-Lagrange on the cost level and a cosine factor of 2. And here in the case of IMAX, we can use a viscosity of 2 or 4. And also we're using a smaller spectral resolution compared to the final visualization. So we divide by 2 the resolution space. And in the case of the semi-Lagrange scheme, we are obliged to use an even smaller spectral resolution and we need to use a second order viscosity to control instabilities. So we have this plot. So here we have the speed up as a function of the error between the parallel time solution and the final solution. The orange line here corresponds to the solution using IMAX on the cost level, using a fourth order viscosity. So we see that we have the better results using this configuration. We have a error that decreases along iterations. And to see the physical solution, so here these plots are the difference between the parallel time solution and the reference solution. So we see that from the initial to the second iterations, we're able to reduce these errors. And here is the 50 iterations. We are able to, compared to the initial solution, we have a much better solution with a speed up, still modest speed up, but still larger than 1 here using also 64 processors. So we see that we're able to reduce these errors using this fourth order configuration viscosity, but we still have some small scale errors which are present in the physical solution. And also the speed up are not that good. If you compare this with the blue curve, for example, which also uses IMAX on the cost levels, but with a second order viscosity, we see that the second order dumps too much the wave number spectrum, so we are not able to converge in the initial iterations. So we need to take some iterations before the error is starting to go left, so to decrease. And the green curve corresponds to the solution using the same Lagrangian scheme on the cost level. So we need here the only configuration which is stable, which doesn't blow up, is a configuration using a very large second order viscosity. So here the plots are the difference between the physical, the parallel time and the reference solution. So the difference between the solution is basically the reference solution. So we're just dumping everything. So we are misrepresenting both small and large scales of the solution. So we're not able to have good convergence results using the sum Lagrange schemes. So well, as a conclusion, the idea here was to verify or to have some indications if we can parallelize in time operational atmospheric models using non-intrusive approaches such as Parareal and MGRIT. So we have seen that the choice of the cost scheme is crucial here. So using IMAX, we can have conversions and speed up if we select if we make good parametric choices and if we use higher order viscosity. But in the case of the same Lagrangian schemes, we are just not able to have good results. So we have instabilities. Even if this scheme is very popular in serial integration atmospheric models because they allow to use very large steps. But we see that we have some analytical and numerical indications that in the parallel time framework we're not able to reproduce this stability. So we also have done some level dependent study of hyperviscosity. So we have seen that we can maintain the accuracy of the final level and use a higher order viscosity when you use IMAX. So we have relatively stable simulations. Well, but the results and both in terms of speed up and convergence are still very modest. So we need to make some more detailed studies for choosing the parallel time parameters and also the viscosity parameters. Here it's important to understand the analytical properties of stability and convergence of the time schemes that we use inside the parallel time methods. And also come back to the first slide. The question here is it's worth to propose new schemes to use inside Parareal or MGRIT. So, for example, similarity explanation methods. So that's it. Thank you very much. You say I'm really sorry because I was sick last week and I didn't recover my voice. So
It was very good. Good job.
So thanks for that. Is there any question already?